start with that. So as I was telling you, so I hope my screen is visible. Let me connect to my stylus over here. Cool. So as these things are visible to you, so we are in supervised machine learning, we are going to talk about logistic regression over here. And a logistic regression, please, I want to emphasize once again that it is not regression, it is used for classification. So remember, don't be confused by the name. Probably we should change the name. Well, frankly speaking, there's a reason why we use logistic regression, because of the logistic function or the sigmoid function that we use for it. Okay, so yesterday we talked a little bit about linear regression over here. Okay, and today we'll continue with that. Okay. Hang on, it's not working. Just a second. Okay, yeah, now it's working. Perfect. Right, so moving on. So let's first try to understand, let's try to see some examples of classification first. So a few examples are in front of you. Classification could be used for to classify, let's say, could be a binary classes. Example over here, if you get an email, if your machine learning model is using, for example, all your email accounts, email, whatever it is, like Gmail, yeah, whatever you use, inherently contains this machine learning model, which will actually classify the emails for you. Is it a spam or is it a ham? Is it a spam or it's not a spam? Okay, so automatically, whatever emails are spam, the machine learning model will ideally identify it, and it will actually put it inside the spam folder so that you don't have to deal with them. Okay. Second example is online transactions. For example, to identify is it for fraudulent transaction or not? Yes and no kind of thing. Third example would be to identify if you get an image of a tumor. So if you get a scan of a tumor, yeah, the machine learning model would ideally should tell you, like, is it a malignant tumor or is it a benign tumor? So benign tumor means the kind of tumor which is not life-threatening. Malignant means which is serious and it is life-threatening. So if you have a benign tumor and if you get it removed, you are safe in some sense, yeah. So however, malignant tumor is those kind of tumors which are life-threatening, like it is really serious. You need to get some serious medical attention, and you have to like, it is kind of spreading kind of thing, right? It is very, very serious, almost life-threatening. Okay, so if we were to identify, so we are going to talk about this example only in our example. So I'm going to use one, theoretically I'm going to use one example, and on for my illustration, I will use the other some of the example. However, it is going to be very, very similar. Okay, so let's try to understand this thing. Let's say we have two classes. So what you have to understand is that one more thing is that machines are not very good with strings and characters. However, machines, when I talk about machines, I'm talking about computers. And when I say computers, I'm talking about all sorts of computers. Your desktop computer, laptops, your smartwatches, your smart glasses, every single thing. Even your smart refrigerators, every single thing which is digital in nature is basically a computer, because it is computing some stuff, okay? Now, they are not inherently good with characters or strings. However, they're extremely well with numbers, and if those numbers are in form of binary format, then very well, it's like the better. So here in our example, what I'll do is that I will actually assign classes to it, and we can do that, right? So just like we assign numbers to random people, we assign nicknames to you here and there, we can assign numbers, right? So we can assign numbers to the Indian cricket team. So let's say number 18 is Virat Kohli, number 10 was Sachin Tendulkar, number 7 was MS Dhoni. Similarly, we can assign numbers to malignant and benign so that it is easy for machines to work with. So we'll say, let's say y is the output that we had to predict, okay? And y will belong to a set of 0 or 1. So where I will say 0 is the negative class, that is benign, and 1 is the positive class, that is malignant. So basically I'm telling you, so I know like if a tumor is positive, sorry, if tumor is malignant, it should be ideally negative. Like if it is life threatening, it should be negative, but I have to find if it is malignant or not. So here I will say that if it is 1, if your output is coming to be 1, I will say it is a malignant tumor. It is a dangerous tumor, life threatening. However, if it is class 0 or negative class, let's say, when I say negative class, it's in terms of the opposite of positive. That's it. It's not like the ethic or morality of that. It's just like, since it is not malignant, I will put it as the opposite of positive. So the opposite of positive is usually negative. Right? So I would say 0 will be a benign tumor. Okay. So imagine like what I'm trying to say is that I want you to imagine like there will be an output known as, let's say, sorry, there's an input, and let's say the input is the image of a tumor. So let's say this is the image of a tumor over here. Uh, okay, so this could be an image. Okay, you will feed this into a machine learning model. Okay, and then you will get an output. So you will either tell me, the output should tell me two things, like output will tell me, is it malignant or not. So here, for in our example, let's say there is an image. So let's say the image is X. I'll feed this into a machine learning model. So in our case, let's say the machine learning model is a function of X. Okay, and it should give me either 0 or 1. Right? So based on that thing. So can you tell me, like, can you guess what are the factors that okay, let me tell you, like, let's not ask you this thing. So I guess one factor which actually determines the malignance level of a tumor, or which determines the fatality of a tumor, would be the tumor size itself. If you've got a bigger like, let's say not you, like if someone has a bigger tumor, that will be more malignant compared to someone else who has a smaller tumor. I know I'm not a medical expert, however, this is a universal thing, that the size of the tumor, as the size increases, the malignance level also increases. Okay, so we can say, like, look at this graph over here. We can say for some reason, and let's say there are two classes over here. Let's say yes and no. I want you to focus over here only. So we can say that up to a certain size of tumor size, I can classify all sorts of tumor as benign. Okay, and after a certain point, I guess I can classify all the tumors as malignant. So as you can see, so probably after this point over here, something like this thing. Probably something like over here, right? So probably at this particular point of X, so let's say this is the X-axis, right? If this is the X-axis, so at this particular point, I will say, let's say this is X critical. Okay. I'm saying that maybe if your X is greater than X critical, I will classify them as malignant. Okay, or in other words, if I will write a simple code, if let's say X is greater than X critical, Y should be, let's say 1. Else, I will say Y should be, let's say, negative, or let's say Y should be 0. Or in other words, if your X is greater than this particular X critical point, maybe you should classify them as malignant level. Now, is this written on stone? No, this is basically a hypothesis that we want to continue with. So when I say hypothesis, it's an assumption that we want to continue with, and that is what is going to happen. So there has to be a threshold. So over here, now obviously, so let's try to understand how this may work. Just a second. Yeah. So let's try to understand how this may work. So let's say, if you remember in our example earlier, linear regression, if we try to fit in a model over here, okay, if we try to fit in a model, what kinds of models are available? Let's try to understand that. Okay, first kind of model, so let me change the color a bit so that it's easier on your eyes. Let me change the thickness also. Okay, so the first kind of model that may come to your mind would be something like this thing. Sorry. sorry, and let me increase this a bit. The first kind of model may come to mind will be something like this thing. Okay. In other words, if this is a straight line, I guess you will agree with me that anything greater than this particular point over here, 0.5, I can classify them as y is equal to 1. Or in other words, if this is a model over here, and if you recall in our example over here, the model was this. I call them as a machine learning model, or it is a model. Okay. And this model is usually represented as y is equal to function of x. Okay, it can be any function. It can be linear function, it can be polynomial function, it can be anything. So what I'm trying to say is that if your this hypothesis, so in our example, let's say our in our other hypothesis is basically h theta of x basically, and if I'm saying that if it is greater than or equal to 0.5 in our assumption, I will classify them as y is equal to 1. Okay, simple as this. And if it is less than 0.5, I will classify them as benign. This is our simple classification that I'm trying to do. Now, as you can see, there are certain problems over here. This may not be the best fit because, well, first for starters, it is not as simple as that. Like how are you going to classify if there is something like like over here, like how are you going to classify this thing if there's a point over here, or let's say if there's a tumor size over here, it will be very difficult to do this thing. So I guess a better fit would over here would be, like if you recall yesterday's example, a better fit instead of a straight line, I had a better fit that was something like this thing. A polynomial curve was there. Similarly, a better fit is available to us in mathematics, luckily, and that fit is known as the sigmoid function. So instead of putting a straight line like this thing, a better fit will be something like this thing, where up till this point. So let me be very careful over here. Or a better point would be something like this. And I guess you will agree, most of you will agree with me, that this is clearly a better fit to my data. Okay. And if I could find the formula for this particular function, let's say this function is known as f of x, and I could say that, hey, if the value of my f of x is greater than or equal to, let's say 0.5, I will classify them as y is equal to 1 or a malignant tumor. And if it is less than 0.5, I can classify them as let's say 0. And the reason I'm trying to make it 0.5 is because my range is between 0 and 1. So I'm choosing the middle value, that is 0.5. It sounds fine to me, like choosing the middle value. So if anything greater than this particular part, 50% will go to malignant. If it is less than this 50%, then go to I will classify them as benign. Okay, and this is the hypothesis that I've started my entire journey with, and that is the idea behind this thing. And luckily, we have a formula for that. We have already in mathematics, we already have something known as a sigmoid function or a logistic function over here. And your logistic function equation will be something like this thing. If you're plotting a graph of z versus h of theta x, or in other words, if it is a function of, let's say, instead of z, let's say it is x, and instead of h of theta, if it is y, then your y will be equal to 1 divided by 1 plus e to the power negative x. This is the the formula for the sigmoid function, basically. Okay, but in our case, I was talking in terms of hypothesis. So I will, in statistics, what we usually say that we talk about hypothesis, or in other words, our assumption that we want to
Sir,
start.
I have a question.
Yeah, sure, go ahead.
Sir, a sigmoid function is an activation function, no?
Yes, good. It is an example. Yeah, it is, in this case, it is an activation function. Good point. So the reason why we say activation function is because it is trying. So we have a hypothesis, and we're not really sure of our hypothesis of now. So what we'll do is that we will plug in the value of this. Like we will plug in this equation. We'll plug in this function to identify we'll plug in this function to find out the classes over here. So the entity which is enabling us, or which is enabling us to identify the classes, or in other words, which is activating our classes. It could be like either it can activate class 1. So let's say this is class 1 and this is class 0. So either it can activate, let's say this activating this bulb over here. So let's say this lights up, or it can light up this bulb over here. Okay. So what is the thing which is enabling it to light it up, or what is the thing which is enabling it to activate, getting activated? The answer is this particular function. And the function that we use in logistic regression is the logistic function or the sigmoid function. Okay, and the sigmoid function will look something like this thing. And the reason that we have chosen sigmoid function is because of its characteristic and its shape. As you can see, as x increases, like as the your z axis, or let's talk about this only, as your z increases, your your hypothesis or your activation function is never going to exceed 1. It will asymptote at 1, or in other words, it will almost reach at 1, almost. Similarly, as x decreases or as z decreases, it is never going to go below 0. It is always so the range is always going to be between 1 and 0 and 1. So in this case, hypothesis h of theta of x will always lie between 0 and 1. Okay, so and this is critical for us because we have two classes over here either. So everything that you're going to find out is either going to be in class 0 or will either going to be in class 1. Now which one to choose, we don't really know. So what we have chosen is that if we have what we'll do is that anything that lies over here, like all the values from here, this part. So let's change, let me change the color. Let's take it as orange. So all the part from here to here, like from here to all the way till here, or other words, this, yeah, this orange line over here, like this. If there is a point that over here, I will classify them into this particular class. Let's say this is class 1, C1. Okay, so that means any value in this particular in this function that is greater than x. So if, so I can write an if condition, like if z is greater than 0, I will classify them as, let's say, a class 1. That is, if there is a, let's take an arbitrary point where z is greater than 0. So let's take this particular point. Okay, I think this point will lie over here, like the value according to the activation function of this particular so the value as per this activation function will be greater than 0.5 in this particular case. Okay, so I will classify them as C1. However, if you've got another however, if your z is is negative, I will classify them as is this particular class over here, the green one. That is from over to here to here. So any point over here that will lie, this is going to be less than 0.5 over here, the middle value, and I will classify them as, let's say, class 0 in our example. Now this is purely hypothesis. We are hypothesizing this thing. We are building a machine statistical model to identify two classes. Does it make sense?
Yes, sir. Got it.
Okay, perfect. So this is the idea, and we are trying to use this idea into our example of tumor size. So as you can see, the axes have shifted. So here the middle point was like at like you were getting 0.5 at z is equal to 0. So but here we are going to change it, and that is fine. You're just shifting the axis, but the function remains the same. So the function's parameters will change here and there a bit, but the function will remain the same. The idea will remain the same. The shape will remain the same. Okay, so moving on. So your logistic regression function will look something like this. Like h of theta of x is equal to okay, let's ignore this part. I don't want to confuse a lot of views. Okay, all right. So over here, as you can see, h of theta of x is what? Is our hypothesis, or in other words, it is our estimated probability that either y is equal to 1 or y is equal to 0 on any value of x. Okay, so whenever we talk about hypothesis, we are basically trying to predict, or we are trying to get an estimated probability of our assumptions. Okay, and this is basically what machine learning is all about. You will come up with an hypothesis, and then you will try to verify that hypothesis. And if your hypothesis is getting verified generally, you will accept that as the ground truth, and you will continue with that. That is the idea behind machine learning, anyway. Now, moving on. Yeah, so let me give you an example. Let me illustrate to you how it might work. So I hope the idea is set now clear to you. Anything greater than a certain critical level, I will classify them as you know, dangerous or malignant nature. Okay, perfect. So let me take a real world example. So over here, I will open a new notebook, and let's say this is workshop day two. Well, I will import all the necessary libraries over here. I will say, okay, let's move first the logistic regression first. Right. So I will import all the necessary libraries, importing all the necessary. Okay, I hope this is getting recorded. Yeah, okay. Right. So I will import pandas, pd, import numpy as np, import matplotlib dot pyplot as plt, and I will use matplotlib and I will say import warnings and warnings dot filter warnings. Right, let me execute this thing. It is getting executed. Yeah, fine. So I will first read a data. So in the data that we're going to use a data set known as coronary heart disease. So your data set will look something like this over here. So over here, we are going to have on two columns, age and coronary heart disease known as CHD. Okay, so this is a heart disease. This is a data set where we are trying to identify the like which age group is going has a more chance to get this to be afflicted with this disease, CHD. So it is a kind of a heart disease. Okay, and I guess most of you will agree with me that usually younger people are safe, like they are, since they have a healthy cardiovascular, like they engage more in cardiovascular activities. That's why their heart muscles are usually more are more, you know, like can resist more, and are in general are more healthy. Okay, are like they're healthier in generally. So what I'm trying to say is that as this these kind of heart diseases, I guess most of you will agree with me, that is usually common in older people. It's not uncommon in younger people, but generally, if I were to draw a graph, it may look something like this thing. So if this is a heart disease, okay, if this is a graph over here, and let's say this is the age, and this is the CHD over here, the heart disease. So I guess most of you will agree with me. It will look something like this thing. So as the age increases, the heart is like as the age increase. Hang on, let me see. Yeah, as age increases, the coronary heart disease, the chance of getting coronary heart disease will increase. So over here, someone over here will have a high will be of more age compared to someone over here who will be having less age. So it is the general data set that we have found over here, and this is the according to the data set that is shown over here. Like majority of the people in their 20s and 30s have zero. So zero means they don't have this heart disease. However, there are some people like when this person who's of age 25 has CHD. But as you go up higher, let's say as you get like more than 50, you will see majority of them have this heart disease. So this is the general idea behind this thing. Okay, and so I will use this data set to work with it. So how to do this thing? I will create a data frame known as CHD is equal to pd.read CSV.
Sir, can we import Seaborn here?
Sure, definitely we can use Seaborn. I'm just using matplotlib for my convenience. That's all. If you're comfortable with Seaborn, you can do that.
Okay, sir.
So I will say cht underscore data, and I will say show me cht dot head. Okay, so this is the first five data set. Okay, all right. So then I will start with the feature engineering part. So let us try to first visualize how this data set may look like. So let us visualize the data to have the insights on building the model. Right. So I will say plt dot scatter. So let's plot a scatter plot. I will say take the age as or take the x-axis as age and the y-axis as CHD, the heart disease, and the data should be the data frame that I've given over here. So in this case, it will be CHD only. Okay, and then I will plot the X label. I will say X label as the age, right? And I will say the Y label to be as the coronary. I'm sorry, coronary heart disease, right? So, and then I will do the pld.title. I'll say age versus coronary heart disease. Right? So if you were to plot, it will look something like this thing. This is the visualization of your dataset. And clearly, as you can see, there are two classes being formed. First class is that people in this class don't have this heart disease, and people in this class have heart disease. And the general trend that I can see is that as age increases, the tendency to get this heart disease increases. However, it is not uncommon for older people to not have this heart disease, and also it is not uncommon for younger people to have this heart disease. However, the general trend is something like this thing. So using our logistic regression idea that we have learned so far, we will try to split the data set. Okay, so here we are going to build the logistic regression model. So to do that, I'll say building the logistic regression model. Right. So I will first split the data set, splitting the data set into training and testing set. So if you recall yesterday's example, I was giving an example over here yesterday, if you recall, about getting calculus and everything. So why to split the data set and everything. So I hope yesterday I told you why do we split the data set and what is the ratio that we usually split. Can I get a yes or no? Did I cover that? Like
Yes, sir.
we
Yes,
covered
sir.
that. So I gave an example of a person of calculus studying 5 days, this and that. Yeah.
Yes, sir. Yes, sir.
Okay, perfect. Okay, so now you know. Now since the data set is not very huge, we don't have a huge data set. So as you can see, it's about 100. It's about 100 rows only. The first row is obviously the title, so there are only 100 rows. I guess it is safe to say that we should split the data set in 70-30 ratio. Right, so we should have, so that's what we're gonna do. So first we'll say, first I will import the train test module, class from the sklearn library. So to do that, I will say from sklearn library, from sklearn dot model
Model selection.
Good, yeah. So if you know it, just guide me. Yeah, you're welcome to do that. Import
Train
train.
test.
Good. Train test split. I'll do that, and then I will specify what should I do. Like, tell me what. Good. Engage with me. What do you think that I should do?
Sir, X train X train X test and then define X test.
Good, good, good. Exactly. That is the idea. But here, first of all, I will have to tell the machine learning model that I have to, what are the predictors? I did not tell you. So, according to you, like, what do you think the predictors are going to be? I guess we could say that the predictors are going to be guesses. The predictor variable, like, what is that? Which variable would predict if you would get a coronary heart disease? It's right in front of you.
So age.
It's the age, yeah. So your predictor variable is going to be the age, and the target variable is going to be the CHD column. So I will have to first mention that. So I will have to first specifying the columns as predictors and a target variable. A column as the predictor, and the target variable. All right. So I will say predictor is equal to in this case is age, right? And my target will be equal to, we'll say CHD. Now we can do that. First, now I will feed this. I will say X is equal to CHD predictor. Okay, and then I will say Y is equal to CHD target. So your X will contain the predictor variable. We'll say capital X contains the
So
predictor.
there should not be the square brackets on the predictor line. I
There
think.
should be actually. There should be. If you remember yesterday. So in our example, we only have one predictor variable. What if there are multiple predictor variables? If you remember in our example of yesterday linear regression that I was talking about, I took first example that I took was of the housing price prediction was sorry housing price prediction was initially I took the size of the house that was used to predict the price of the house. But what if there are more than one factors? Like for example, number of bedrooms. Okay, in that case we will have to pass in a list. So usually we, for the predictor variables, we pass in a list over here. Okay, we, there is very much possible, like it could be like instead of like up on apart from age, there could be other factors or other predictive variables. In this data set there is none, such as let's say age, and let's say I don't know, the the amount of exercise. So if there was a column known as amount of exercise per week, that a person gets, that will also influence the CHD. Yeah. And
Sir,
if that,
sir, you mean if we have many attributes to our data set, then we have to use that square brackets.
the square bracket is what? This is basically a list over here.
Yeah, yeah.
So it's a list. Okay. So it is possible. So your list may contain one item or it may contain more than one item. So we usually make it a habit to pass in a list as the predictor variable. But usually the target is going to be only a single variable only. We don't bother with the target. We don't bother to put it inside a list because it's only going to be one. But predictor can be either one or more than one. So that is why we usually enclose this inside a list. And the way to use list in Python is using square bracket. Make sense?
Got it, sir.
Okay, right. And call me Aben. It's fine. Don't call me. So sounds weird to me. Contains, and Y contains the target label. Okay. And then here now I will split the data. Splitting the data into training and testing set in 70/30 70 is to 30 ratio. So I will say x underscore train x test.
X underscore test.
Yep. Y train
Y train Y test
y test is equal
equals
to
to X comma Y.
no train test
Train
plate.
test.
Train test plate. We'll say x. We will feed in the predictive variable or variables and y variable. And then I will say what is the testing size that I should give. So I will say test underscore size is equal to 30%. That is 0.3.
Point.
Okay. And then I'm saying random state is uh, equal to 0. Okay. After doing this thing, I have executed this thing. Now let me print the shape of x train and y train just to verify things. So I will say print. Let me zoom in a bit. I will say print shape of x underscore train uh, is equal to x underscore train dot shape attribute. Okay, and I'll just copy this part. I'll paste it for shape of x test y train.
Sir, if we don't write random state, then what will be the default value of it?
What do you think will happen?
Sir, I think 101 maybe.
Okay, what do you think the random state is gonna do? What do you think? What is the guess?
Random state basically splits the data in the same manner. mm, when we split again rerun the cell.
Yes, exactly. No, well, the truth is the random state actually tells you, like which portion of the data set should you take as the testing data set. Okay, so like should you select it randomly or not? So if you're saying random state is equal to 0, then it won't select it randomly. It will select a certain 30% only certain 30% only. Probably the first 70% will be the training, and the last 30% will be reserved for testing part. So I'm saying random state is equal to 0 because I just wanted to do it like that only. Okay, so when I execute this part, I will get something like this: 71, 31, 70, 0, 30, 0. So in other words, what I basically did was I had a data set. In my data set, it looks something like this. Why is not working? Right. So I had a data set. So in my data set, there were 100 rows. So 1, 2, 3, all the way till 100. All the way till 100 was there. Okay. So what I did was, this was X train, if you remember. This was age, and this was CHD. This was the idea behind this thing. Now what I did was I selected the first 70. So the 1, 2, 3, 4, all the way till 70 were reserved for training purposes. So this was age and this was CHD. Okay, so both of them were selected over here. Now this was used for training purposes. So in my case, this is what? This will be X train and this will be Y training part. Yeah. Now, the rest 30 was reserved for the testing purposes. That is, the machine learning model will will train on this data set. And then let's say the machine learning model has learned, it will be provided. So let me change the color. It will be provided during the testing phase, it will be provided a data set. Only the X part will be provided to it. So that is only the X test will be provided. That is from, in our case, it will be 71, 72, all the way till 100. Will be provided over here. And then it will give you a prediction. So that prediction will be Y pred. Okay. So this will be akin to, it will have like 71 Y pred, let's say 71 prime, 72 prime, so on till 100 prime. Okay, this was the prediction. You will compare it against the Y test taken, like there will be in the data set, say from 71 till 100, there will be X value and also the Y value. You're testing it on X value and you're hiding the Y test value. These values you will be hiding over here. Okay, and you will be getting the Y prediction, and this Y test will contain the original data set. Now it will check how off are they. Like, so it will find the difference between the predicted value and the testing value, and it will calculate a score. If your score is high, that means y predicted value and y testing value are very, very similar to each other. That means your machine learning model is able to perform correctly on unseen testing data set. That is the idea behind this thing. So if you would see your this the shape, that is why your X train and Y train, hang on, let me see. Yeah, that is why your there's something a problem X test. Yeah, yeah, exactly. So that is why your X train and Y train, sorry, X train and X test will contain will contain this shape. That is, there are 70 rows and one column, and X test will contain 30 rows and one column. However, this is a vector. So this is the so X train and X test is a matrix, but your Y train and Y test is, hang on, this is Y test. Contains Y test is a vector over here. Right. Moving on. So right now, we will try to build a machine learning model. So here we will try to build the machine learning model. To do that, we will have to import the required libraries and the required class. Just give me a second. There's someone at my door, so give me 2 minutes, please. I'll be back in 2 minutes. Yeah, apologies for that. I actually go and open my door. So yeah, let's continue. So we will import the required class. So in our case, the required class is from sklearn dot linear model
Linear model.
import logistic regression. And then I will create an object, creating the object of this class, the object of the class logistic regression. As you can see, I'm also documenting my code. So it is a good habit to document the code. So I'll say model is equal to logistic regression. Okay, and then I will fit the model. So yesterday I already talked to you about what is the meaning of the fitting the model. So I want to repeat that. Show that training data. And to do that, I will say model dot fit the X train and the Y train over here that I've talked to you about. So here I'm going to fit the X and Y part, the predictors and the target variable, but of the training data set that I've already split it over here. So okay, so then I will get the intercept. So getting the intercept and the slopes of the model. So to do that, I will say print me the intercept. I'll say model dot intercept underscore. I'll say print slope. So slope or slopes, it could be either. I'll say model dot coefficient underscore. Let's see if it works. Yeah, it is working. Perfect. So as you can see, it can, since in our case there is only one predictor variable, there's only going to be one slope. but that is why it is getting in like the output is also inside a list. But in this case, the intercept is only going to be one. Yeah. So now we will try to predict the probability for each class, for each of the class labels in the final class for the new data. So to do that, it will say, let me type what I said. So I'm going to say predicting the probabilities, I don't know, yeah, for each of the class labels and the final and the final class for a new data. So it will look something like this. Then I will say test dot. So here I am actually giving a random value over here. In other words, now my machine learning model has already learned. Now I will give a random value, let's say of 29 age, and based on the data, like based on the data that has learned from, it should predict if it is correct or not. So if I were to ask you, based on this data, a person of age 29, what should be his condition? Should it be zero or should it be one? CHD. Like, should we predict if the person would get CHD or the heart disease or not? Yes or no? What do you
No,
think?
sir. No, sir. It
Zero.
would be zero.
Zero, right? Good. So that is what we are going to see if our model is working or not. So I will say np.array. I will given the array 29. Okay, and then I will reshape it. Reshaping because I want to give in a column matrix. So I will say -1, uh, uh, -1. So your test will look something like this thing. Test.shape will look something like this. So here I will say, now I will say print the probabilities. I will say print the yeah, probabilities. So spelling correct? Probabilities, yeah. Probabilities is equal to model dot predict underscore proba and pass in the value test. Okay, and then I will say print. I want to predict the CHD value. That what the CHD predicted value. That would be equal to model dot predict the test. And let's see if it's work or not. If it works or not. It is working. So the probability of the person not getting the of getting zero is about 91.8%, and of getting a CHD1 is about 8.1%. And the predicted CHD value based on that probabilities, we have put the person in the class 0. So this is how your logistic regression would work. Okay, and if you wanted to visualize this thing, you will let's try to plot it. Okay, so for plotting part, we'll say this thing. We'll say predict underscore test is equal to model dot
So
predict.
can you explain the first part,
Which part?
first line, first line of the previous cell?
Yeah, I'm creating an array over here. The array contains only one value. So for example, if I were to add, let's say, another value, let's say 20 comma 21, whatever it is. Okay, it is going to give me an error. Hang on. So here I will uh, just, I should have probably started with that. I'm creating an array over here. Okay, and the array contains how many elements? The array contains only one element over here. Okay, but usually what we do is that I want my array to be in a column form. Okay, now if I were to normally insert an array, it will be in a row format. In other words, basically what I'm trying to say is that um, what you have to understand is we usually prefer to give all the values in the format of a column. So where is it?
Got it, sir. Got it, sir.
Got it?
Yes, sir. Yes, sir.
Okay, so if there are, let's say, two values, let's say 29, 30, 32. These are the values. Now this is in the form of a row. What computer is expecting is in the format of a column, 29, 30 and 32. So that's why I've reshaped it. Now I only have one thing, right? So I only have 29. So that's why I just like reshaping it or not. I let us see if it makes a difference or not. So if I were to remove this part, yeah, it is expecting an error. So let's see. Look at the error. The error says expected 2D array, but you gave me only 1D array. Why? Because I only gave a one-dimensional array over here. Okay, makes sense. So what if I gave like this thing? Will this work? Yeah, it is now working. So here, since I gave only one-dimensional array, so if you recall, okay, if you may not know this thing, one-dimensional array is known as a vector. Okay, a two-dimensional array is known as a is
Met-
basically a
Metric.
matrix, and well, there is a better way to say this thing. And a three-dimensional array we usually call it as, or like more than like two-dimensional array, we will call it an ND array in NumPy, or broadly speaking, we called it as n-dimensional tensors. A zero-dimensional tensor would be a scalar value. A one-dimensional tensor would be a vector. Two-dimensional scalar tensor would be a matrix, and three-dimensional would be a tensor, and so on and so forth. So it's basically a data structure to store values, nothing else. So your list can store value, your dictionary can store value, stacks can store value. So these are some data structures that the computer is expecting to store the value. So you would say np dot. So either you can do this thing, or I can say reshape. Give it a one, so to make it 1 comma minus 1. Okay, perfect. So here now I will say plotting predict test is equal to model dot predict prober. I will say x underscore test, and excuse me. So what am I doing? Okay, let me write the comment also. I'm getting the probability for class label, for the class label 1 for all samples. Okay, and then I will try to plot it. I will say plotting the actual class labels for the target values for the samples. To do that, I will plot a scatter plot, same as before. I will say scatter, but here this time I will feed in the value for the I will say x test. I want the x test, and the test is going to be age, and here the it is going to be y underscore test. Then the label is going to be, I'm just going to label it actual target value. And here I'm going to plotting the predicted. So I want you to make sure it is the predicted, and this is the actual one. Predicted probability for class label 1 for all samples. Okay. So that I will say plt.scatter. Inside this, I will give the same thing. So x-axis is going to remain the same. So I will say x test age, comma. Here I will say predicted test, comma label is equal to probability, or let's say probability of class 1 class 1, yeah. Marker, let's say marker is equal to O. The color is equal to, say, orange. Wow. And let me add the labels as well. So adding the labels and the the labels title and the legend. So it's pretty simple. I will say plt.x label uh, age plt.y label chd chd. The title would be uh, prediction probabilities, and your plt.legend will be, yeah. So once you draw this thing, this is what you're gonna get. So the blue one is the actual data target value, and this yellow one is the predicted probability. So as you can see, it is forming a sigmoid function. So this is the idea behind this thing. So this is a very simple example of how your logistic regression would work. So I gave you a theory and the practical application over here. So I hope all of you understood what logistic regression does. It is used for classification. So I give you an example: binary classification.
Sir, what does plt.legend do?
Legend is this thing, man. This small patch of text that tells you what is what. So if you remove this thing, let's make it common. It will remove that. You won't know what is blue and what is yellow. So you're adding legend, and legend will fetch the values from this label. So you have to mention the label. So as you can see, this label says probability of class 1. So it will execute. Let's execute this thing. It will tell you, okay, it will fetch the value. It will say, okay, so yellow values over here, so the orange values over here, which has the marker O, it has the label probability of class 1. So in the legend, you will fetch this text over here. Make sense? Same from this particular part.
Got it, sir.
Okay, perfect. But who's this person who's interacting? It's Rupam, yeah?
Sir, Ankit Pandey.
Okay, Ankit, yeah, okay, it's perfect. Well, thanks. I appreciate your interaction, though. Thanks for that. So I guess we can. Are we all good? I guess of the Ankit is the only person who's responding. Please type in the chat window should you have any doubt, anything. You can see. Open the chat window. Any questions, concerns, queries? Nothing, I guess. Okay, perfect. So what we'll do is that we'll take a short break for like it's already 1 o'clock. Marker. Okay, yeah, perfect. I'll explain the marker. The marker is like this thing, man. This thing. This is like I told the Jupyter notebook that I want the marker to be in the O shape. If I were to give, let's say, some other shape, let's say some star shape, it would have mentioned this in the form of stars. If you want a plus shape, you can do that as well. So these are these things. Visualization purposes. Now it looks funny, right? So I want it to be 0. So marker, if you leave it as default, it will naturally give you this thing only. Like the default marker is 0, the O only, like O kind of structure, like little full circles. Anything else?
Yes, I
No,
got
sir.
it. Thank you.
Okay, perfect. So I guess it's already 1 o'clock. I'm pretty sure all of you must be really hungry. Let's take a lunch break for how long? How long do you need the break for? Half an hour, 45 minutes? What would you prefer?
15 minutes, sir.
15 minutes? Okay, someone says 45, someone says 15. Okay, okay, let's see what's gonna happen. The thing is, I am left to teach you k-means algorithm. Okay, so okay, let's take a vote. So as 2 people for 30 minutes, one for 45, one for 15. Other people, please vote. Let's see that. Okay, one. Okay, so Heyman says 30. So Heyman says 30. Then they'll agree. We're going to say use 30. So it's already 1:05. Let's take a break till 1:35. Okay, so we'll continue at 1:35. Sounds good. We'll continue with the unsupervised machine learning.
Okay, sir.
Okay, right. Perfect. Thank you all.